Afternoon class. In today's video I wanted to talk about electric power. So in this video what I'm going to be talking about is this equation here, P equals IV. What the other thing I can do is to utilize Ohm's law here with voltage and turn it in because V equals IR. So you would get P equals I times IR, which gives you I squared R. So I just wanted to break that down to show where some of these equations come from. Now, the main thing that I wanted to cover in this video is to talk about how is power transmitted and what choices you could make if you were to decide to actually transmit power across something like a power line, for example, like in my attempt at drawing one. So if you're transporting electricity over a large distance, what you can do is you can either send a large current or a large voltage across the power lines. Now, which choice really matters? And in this case, there is actually a difference, and it has to do with how power is carried through these wires. So one thing you have to understand is that as power is getting carried through the wires, when the current goes up, what happens is that it starts to heat up the wire a lot more. You can kind of think of it like water in a pipe. The faster that you move the water through the pipe, the more it can start to rub against the inside of the pipe. Now, don't get me wrong. There's most of the time, for most speeds, water running through a pipe doesn't cause much friction at all. But at a certain pressure, after you pump water enough through a pipe, and as you force it through the pipe, what happens is that the pipe will eventually start to rub against the water will eventually interact with the pipe enough to make the pipe hot, and that's a problem. You don't want that in your piping system. So a lot of times what you'll do is in order to get that pipe to flow a little bit better so that it doesn't heat up as much as you want it to, what you do is you make the pipe bigger. So if you've ever noticed that maybe if you've ever watched Teenage Mutant Ninja Turtles, you might have seen that those sewer pipes are absolutely huge. They're about as tall as this room. And that's actually because the volume of water that would be going through those, especially on a municipal level, would be so huge that because you need that, all these little pipes are pumping in water into one large pipe to go to that one sewage treatment plant. That's kind of the same thing that's happening in these power lines. You can either send a whole lot of current through these power lines, and the problem is you're going to actually, by doing that, you're going to have a lot of loss due to heat and all these wires that are heating up. And of course, if you have wires that are heating up, they're going to break a lot faster. So, two problems that you have to deal with. However, and the thing is, you can't with these wires, you can't really make them bigger. Like, you can't stretch the wire out to make the wire bigger for more current to flow. But what you can do is decrease the current by increasing the voltage. So if you decrease the current, you increase the voltage. The power stays the same because these two are inversely related. And if you send the voltage across, what you're doing is you're essentially trying to widen the pipe a little bit so that more current can flow, but it won't flow as fast. It'll flow slower, but it'll still get to where it needs to go here at the end of the line. So that's one of the things I wanted to go over. And of course, if you wanted to see a little bit of a bullet pointed portion of what I just said, it's all right over here. So that was to get you the idea of how do we transmit power. So as you think about how you would transmit power, especially over vast distances, those are some of the technical problems that you're going to have to deal with. So that concludes this conceptual basis on electric power. Good luck in your studies, and may the force be with you.